Okay, YouTube, in my last video we solved pretty simple logarithmic expression equations. In this video we're going to introduce, or at least let's just say highlight a few equations here that I'll go through and solve with you, in which using your typical methods aren't really that effective. So first things first, when we solve a logarithmic equation, what we're trying to do is we're trying to solve for an unknown that exists inside of a logarithmic function. So the first thing we want to do is isolate the logarithm itself. You'll notice that when you have more than one logarithm, one really good method for solving these is to use the one-to-one property, and that basically says log base b of x is equal to log base b of y if and only if x is equal to y. And so essentially that method is, if you have more than one logarithm, we'll just drop one on one side and drop one on the other. So we could essentially subtract log base 10 of x plus 1 to the other side, but what you get is an expression that looks like this: log base 10 of 5x is equal to 2 minus log base 10 of x plus 1. And so you can see here that we don't have a logarithm equal to a logarithm. We have a logarithm equal to 2 minus a logarithm. Even though they have the same basis, I can't equate the stuff that's inside of their argument here. So what this means is we're going to have to try to isolate these, and we're going to use what essentially we have as properties of logarithms. So one property of logarithms says this: if you take the log base b, we'll say base b, of a product, what we can do is we can actually rewrite that in an expanded form as log base b of u plus log base b of v. And this is what we refer to as logarithmic expansion. The nice thing about expansion is that it works both ways. So if we ever see two logs with the same bases being added together, then we could say, well, we could rewrite this as a single log of what? Well, of these two arguments right here. Let me switch colors. These two things, whatever they are in here, being multiplied together. So when we look at an expression like this, what we're going to do is we're going to condense this into a single log, and what we get really is this: we get log base, now this is log base 10, I'm going to put a 10 just to highlight this fact, but we'd say of what? Well, of whatever was in here times whatever's in here. So what we end up with is we get 5x times x plus 1, and this is all equal to 2. And so you'll notice that we rewrote both of these logs as a single log base 10 of their two arguments being multiplied together using our condensing of logs, I guess, expression, property. So we have something here where we're going to need to simplify a little bit, but what we can say here with 100% accuracy is we can distribute this 5x through here, and so we get log base 10 of 5x squared plus 5x, and this is equal to 2. So now that we have this logarithmic expression isolated, what we're going to do is we're going to raise both of these sides to being the exponents. In other words, we have a logarithmic thing. We're going to undo it with an exponential expression, so we're going to exponentiate both sides. 10 to the power of the left side is equal to 10 to the power of the right side. So essentially what we end up having happen here is we get our exponential thing cancel out with our logarithmic thing, since they're inverses, and get left with just what the exponent was, which was 5x squared plus 5x. On the right side, we get here 10 to the second, which is 100. So now, solving something like this, what we're going to do is we're just going to do our basic algebra, which says, well, I've got a second degree thing. I can't get x by itself here easily. We've got x to the second, x to the first. Let's set this equal to 0 and try to solve this by factoring if we can help it. So we say 5x minus 100 equals 0. I notice that the left side has a greatest common factor of 5, so now I have x squared plus 1x minus 20 is equal to 0. And if I divide both sides by this 5 here, notice that 0 divided by 5 is just 0. So really what follows is that we have this x squared plus x minus 20 equals 0. And a trinomial of this form, we would say that we could factor this, and two factors of the product of negative 20 would mean that these binomials have different signs, a plus and a minus, and they add up to be a positive 1. So I can think of two factors here, it'd be 5 and negative 4. And so since these are the factors, we would say, well, then either x plus 5 equals 0 or x minus 4 equals 0. But basically that, x is either negative 5 or x is a positive 4. And so one thing I want to make very clear here is this. I'm going to write this out over here, negative 5 or a positive 4, is that we want to check our answers all of the time. So let me try to block this off here. We won't go through all the examples together. I'll go through 2 with you. But we say if we plug this back into the original expression, check this out. We get log base 10 of 5 times, let's do negative 5 first. So in negative 5 here. And that was plus log base, and we have x plus 1 here. So we have negative 5 plus 1 is equal to 2. Notice that we get log base 10 of negative 25 plus log base 10 of negative 4 equals 2. And what I basically want to point out here is, I would say this: we can never take 10 to the power of something and get a negative output. So what you're looking at here is a situation where we'd say negative 5, we're going to give this a name, we call it an extraneous solutions. In extraneous solutions, we always tend to get, we don't always, but we tend to get extraneous solutions when we have to solve squared type relationships here. So what you end up with is a negative value. It's not going to work in the original expression, but algebraically it works out. So I do want to check 4 here. We say log base 10 and we have 5x, so we say 5 times 4 plus log base 10 of, and we had x plus 1, so we say 4 plus 1. It should be in blue here, that plus 1, and this equals 2. So basically we get log base 10 of 20 plus log base 10 of 5 equals 2, and I can prove that this is very true because if we condense these logarithmic expressions here, we get log base 10 of 20 times 5, putting these back together, is equal to 2. In other words, log base 10 of 100 is very much 2 because 10 to the second power equals 100. So 4 would work. So 4 is not extraneous, and as a matter of fact, 4 is the only solution to this equation. So these other expressions that you're seeing here, at least this one over here, you would need to condense these two logarithms. This one that you see here in the middle, I do want to point this out. We say log base 2 of x plus 2 is equal to log base 2 of x squared. This is already a one-to-one type of situation. We have a log base 2 equal to a log base 2. So what this means is we can take their arguments here and say, well then, this would only be true if and only if x plus 2 is equal to x squared. And so essentially what I wanted to do here is I just wanted to run through another equation where we're going to practice some essential algebra skills that say, we'll just set this equal to 0. We'll set this equal to 0 and we get x squared minus x minus 2. And again, we'll factor this expression in here. We say x, this is all equal to 0. And we say that two numbers that multiply out to be a negative 2 that add up to be a negative 1 are negative 2 and positive 1. And furthermore, we say if that times that equals 0, then x minus 2 equals 0, or x plus 1 equals 0. And it follows that we get x equals 2, or x equals negative 1. Now, with logarithms, I can tell you that most of the time it's going to be the negative value that fails when you plug it back in, but it's not necessarily always true. So check both of these solutions now by plugging them back into the original expressions and see which ones maybe work and which ones don't work. I suspect that it's going to be just the positive 2, but like I said, you need to plug it back in to check. But that is how you solve a couple of a little bit different logarithmic expressions using properties of logs. Cheers.